Okay, let's start. So hello everyone, I'm Jan Kronqvist. I'm an assistant professor at KTH at the Department of Mathematics, and I'm a Digital Futures faculty. So today I will talk about our C3 AI project, AI Techniques for Power Systems under Cyberattacks. And this is a collaborative project, and here are pictures of all the PIs. So first we have Javad Lavey at the University of California, Berkeley, Soumaya Sujudi, also at the University of California, Berkeley. I'm at KTH, Stephen Lowe at Caltech, and Jeremy Lawrence at the Electric Power Research Institute. And this project is started now in the summer of 2022. First, a brief motivation to this research. So in order to improve efficiency, resiliency, and sustainability of power systems, the operation of power systems is now shifting to become more data-centric and data-driven. And this is a good thing. But this can also lead to system vulnerabilities. So for example, the manipulation of data by a malicious actor can really tamper with the operation of the grid and result in catastrophic damage. And the goal of our project here is to develop frameworks and methodologies to protect power systems against such malicious attacks. And our project, it consists of 4 main tasks. And the team at KTH, we are really focusing on this third part, learning robust deep neural networks. And this is what I will focus on in this presentation. So deep neural networks, I'm assuming that you're all familiar with this topic, but I will still provide a bit of a background information. So I will explain this research from an image classification perspective, but I really want to point out that this research, it is not limited to image classification. And my team at KTH, we are focusing on rigorous methods for identifying and analyzing weaknesses in DNN systems and how to construct robust DNNs that we can trust. And I will explain more what I mean by this trust. So deep neural networks, as many of you are aware, they have achieved very impressive performance for classification tasks, such as image and speech recognition. And here I have an example of the so-called CIFAR 10 dataset, which consists of images from 10 different categories. For example, cats, birds, cars, and airplanes. And current state of the art is able to achieve about a 99% correct classification, which is really impressive because many of these images, they are not easy to tell what they are by just looking at them. But can we trust DNNs? This is the question that I really want to focus on in this presentation. And this is a very, very relevant question because quite often DNNs, they're used in more or less a black box fashion, where we just feed in some data to the network, we get some output, but we don't fully understand what is happening inside the neural network. And it is well known that DNNs, that they can be unstable with respect to adversarial perturbations. And here I have a classical example of this, where we have a neural network that is trained to perform very well on image classification. So if you take this image to the left, feed it through a neural network, then it will classify it correctly as a duck. But now if we take a tiny, tiny perturbation, add this noise to this image to obtain the image to the right, and here we are not really changing the image, or at least I can't really tell the image to the left apart from the image to the right. But now if we take this right image that is slightly modified, feed it through the same neural network, then it will be misclassified and it will be classified as a horse, which it is clearly not. And this gets even worse. There are more extreme examples. So here we have another case where we have a neural network that is trained to perform very well on recognizing these handwritten numbers, and it classifies all of these correctly. But now, by just changing one single pixel of these images, we're able to get them all misclassified. And this is what I mean when I say this network, it is not robust. It's not robust because we can just change one single pixel to change the classification. And this gets quite scary when we start thinking about safety critical applications. For example, in self-driving cars, where we want to identify traffic lights and signs. So here we want to be fairly confident that if we look at a stop sign, that we are able to classify this correctly. Now think about what I told you on the previous slide, that we were able to get a misclassification by just changing a single pixel. Then imagine what might happen if someone goes and draws something on this stop sign with a permanent marker. So how to obtain safety guarantees? This is really a relevant question and a topic worth studying. And here we can use mixed integer optimization to analyze DNNs. And we will use this to analyze if we can trust network predictions and also to obtain some sort of understanding of the network predictions to give us some sort of explainability and interpretability. And for analyzing DNNs by mixed integer optimization, we build upon techniques that we have previously developed for optimizing overtrained neural networks. And this project, it was a collaboration with Imperial College, with the following people. And this was a very successful project, and we were able to develop new methods to solve these optimization problems much more efficiently. So in robust verification of trained DNNs, we are focusing on two main questions. Can the network produce forbidden outputs, and can a tiny perturbation cause a misclassification? So here we take the input image, and we don't really consider it as an image, we just consider it as a long vector. And what we ask here is, does there exist a small delta, a small perturbation delta, that if we add this delta to the reference input, that it gets classified differently? And this can be encoded as a mixed integer linear programming problem for networks with the so-called ReLU activation function. And the advantage of this is that it gives us rigorous proofs. Either we find the perturbation that causes the misclassification, or it proves to us that such a perturbation does not exist. So the ReLU activation function, this is one of the most commonly used activation functions. It is simply defined as the maximum of 0 and an affine function of the inputs. And by using the following linear constraints and a binary variable, we are able to represent the node exactly as a mixed integer linear programming problem. And if we use this representation for each node in the neural network, then we are able to obtain an exact representation of the input-output mapping of the DNN. But I also want to mention that solving such optimization problems, this can be quite challenging. So here I want to illustrate how we can use these optimization techniques to analyze DNNs. So here on the left, we have some minimum perturbations for misclassification. So what we are looking at here is how little can we change this original image in order to get it misclassified as a number 4. And we can do this with regards to different measures. So here on the right, we are looking at the characterizing features of a DNN, of a specific DNN. So for example, we can look at which pixels are the most important pixels to be colored black here in order for the image to be classified as a number 3. And as I mentioned, these optimization problems, they can be quite difficult to solve, and this is mainly due to a weak continuous relaxation. So the way we solve these optimization problems is that we first relax the problem. We allow the binary variables to take on fractional values between 0 and 1, and we split this up into a sequence of optimization problems where we eventually force the variables to be either 0 or 1. But when we first relax the variables, then we lose the exact representation. Then we don't know exactly what is the output for a given input. We just get an upper and a lower bound of the value of the output. So this is shown in the picture here on the left, where the orange surface represents how the output of a neural network changes with the inputs. And the blue and green surface, they represent the upper and lower bounds. So when we get weak bounds, it can result in a huge number of subproblems in order to get an exact representation of the neural network. And in practice, we may not be able to go through all of these subproblems. There are also other formulations, so-called ideal formulations, that can result in a significantly tighter relaxation, tighter upper and lower bounds. And if you use this, we should theoretically be able to solve the problem by exploring fewer subproblems, but these problems, they grow exponentially in size. So the number of constraints and variables, these can become really massive. And for problems of industry-relevant size, we are typically not able to use these formulations. So what we did was we developed some intermediate formulations that captures the best of both worlds. We get a stronger relaxation, but we still get subproblems that we're able to deal with. And this gave us speed-ups of orders of magnitudes. And this allows us to optimize our DNNs of industry relevant size. And this work, this was presented in Europe in 2021 and also at the CPAOR. And just a quick summary. So from this presentation, I really want you to take away that we can use mixed integer optimization to analyze DNNs. We have efficient methods for identifying issues and security risks in trained DNNs. And the goal of this project, it is to use these methods for analyzing DNNs to train robust and secure DNNs. And this is a work in progress. And I'm happy to tell you that we have several very promising ideas, and the initial computational results is also looking very promising. So I'm greatly looking forward to the next year, where I will be able to share with you the outcomes of this project. Thank you very much for listening to this presentation.